Hey guys, so in this video we're going to talk about the manometer, which is a type of pressure gauge. Let's check it out. Alright, so manometers are pressure gauges, and pressure gauges are just devices that use height differences. For example, here's this gray liquid. Notice that there's a height difference between here and here. You can come across to this side and you can calculate this height difference. You can measure this height difference. And if you know this height difference, you got it, you can use that to calculate pressure using this equation right here, where h is my measured height. Okay, so a manometer has some weird shaped tube. Typically it's making some sort of U shape. It has a gas on the left, let's call this gas 1, has a gas on the right, gas 2, and it has a liquid in the middle section here. Now sometimes that gas is simply air, or sometimes there's no gas at all. It's got vacuum, which is what's going on here. Also, this top part here could be closed as it is, or it could be open. And if it's open, it's exposed to whatever air, whatever gas is right outside of it, which most of the time, if it's open, we're gonna have the atmospheric pressure pushing down on the open side. Now, this first two examples here are pretty trivial. Let me write this here. These two are pretty trivial, pretty silly. The pressure is the same, therefore the height will be the same. So here there's no pressure, so the pressure is 0, and here the pressure is 0 as well. So because the pressure at the top of both sides of the liquid are 0, because they're the same actually, the liquid's just gonna level itself out. Same thing here, it's open, so you have the atmospheric pressure here, which is 1 atm, the standard one. So if you have 1 atm pushing here, and then you have 1 atm pushing here, the liquid will level itself out. So equal pressure means equal heights. Okay, now before we move into the second one here, which is where it actually gets interesting, where it actually gets useful, I want to make a quick point here. Remember that the pressure in a gas doesn't change much. Let me write this here. Doesn't change much with height differences or depth differences. What does that mean? That means that if the pressure here is 1 atm, the pressure here is also going to be 1 atm. The pressure here is also going to be 1 atm. So it's the same pressure everywhere. This is not the case with liquids. With liquids, pressure changes pretty rapidly, even with subtle differences in heights. With gases, the pressures we're going to consider not to change in height differences that are this small. Okay, so let's look here. So here you have pressure difference. You can come across here. So here it's vacuum, so the pressure here is 1, and then 0, and then the pressure here is 1. That's why the liquid looks like this, because here you have a 0, so it's not pushing at all on this column, but this column is being pushed with 1, so there's more pressure here, so it does this. Okay, so that's why there's this difference. Same thing here. This here is closed, this with no air here, so it's vacuum. This is open, so you have atmospheric pressure, which is 1 atm. But on the other side, there's a gas that has 2 atm. So same thing, this is pushing harder, so it's going to do this. Cool, let's do a quick example. This is very straightforward. Here we have to find the density of a known liquid. You pour some of it into a manometer. And eventually, by the way, you're going to want to calculate the density of that liquid. So let me just write here, what is the density of the liquid? You're putting it in a manometer, just as shown above. And it is closed at one of its ends, and it's a vacuum there. So let's draw a manometer similar to what we had before. By the way, the bulb sometimes could be sideways. It really doesn't matter. And it's closed here, and there's no pressure here. Pressure is going to be 0. And it has 1 atm air, so the pressure, it doesn't matter that it's air, by the way, it just matters that the pressure is 1 atm at the bulb side. This is called the bulb, usually where you have the gas. You measure the height difference to be 60 centimeters. So the way I like to approach this, I think of the two sides being the same, and then I look at the pressures. This is 0, this is 1, so it's going to do this, right? So you can imagine that they were initially the same, but then now this rode up a little bit, and the other one rode down a little bit. So that's this. It says here that the pressure, the height difference, I can go across to the other side, and this height difference here, h, is 0.6 meters. And we want to know the density of the liquid. So every time you have a height difference in a liquid problem, you're going to write the pressure difference equation. So P bottom equals P top plus rho G H. Remember, this is also referred to as the absolute pressure, and this is also referred to as the relative pressure, and this is also referred to as the gauge pressure. In this case, we're looking for rho of the liquid. So pressure at the bottom is always this pressure over here at the bottom of the column of liquid. Now I can go over to the other side. Let's give these names. Let's call this pressure 1, pressure 2. Let's call this pressure 3, and let's call this pressure 4. Pressure 1 is simply 0 because it's touching vacuum. Pressure 2 is the same thing as pressure 3 because you are within the same liquid at the same height. So I'm going to write this down because it's very important. Within the same liquid, at the same height, you have the same pressure. That means I can go across here and say, hey, P2 is the same as P3. And by the way, P3 is touching the air, the gas here, so it's the same as P4. So really P2, which was the bottom pressure, is the same as the gas on the other side here. It's P gas of the second gas. So when I say, when I have P bottom here, it's simply going to be 1 atm. You go all the way across, and P bottom is simply 1 atm. I'm going to rewrite this equation here, 1 atm. The pressure at the top is this over here at the top of the column. So that's going to be 0 atm, and then rho, which is what we're looking for, and then gravity, 9.8, and the height, which is 0.6. Notice that I have all the numbers, so I can just move some stuff around to find density. But before you do that, remember that you cannot use 1 atm in equations. That's just a shortcut unit. In reality, you have to write this in Pascal, and 1 atm, you have to memorize this as 1.01 times 10 to the 5th Pascal. So I'm going to rewrite this as 1.01, or sometimes it's easier to just write the big number, 101,000 Pascal divided by 9.8 meters per second squared. And I'm just moving stuff to the other side, 0.6. So this is my density, okay? And by the way, if you multiply all of this, you get 17,177, 17,177. And the units, this is pressure, this is density. So the units, since I'm using standard units everywhere, you're gonna get the standard units of the density, which is kilograms per cubic meter, okay? So that's it, that's the answer for part A. All we had to do is plug it into the big equation, and we had all the numbers, just had to move some stuff around. Let's do part B, and I'm now gonna get out of the way here. So for part B, it says you replace the 1 atm air, so whatever air, was here, air, you replace that with an unknown gas. So what does that mean? Well, remember the pressure, you knew this was 1 atm. If you're replacing it with something else, you no longer know what that pressure is. And that's in fact what the problem is asking. What is the pressure of this new gas on the right side? Okay, now you replace that, and remember that this pressure is the same pressure as the pressure at the bottom. So this is going to be P bottom, and you have to figure out what P bottom is. Now, keep in mind that these problems aren't going to say find P bottom or find P top. Sometimes they will, but a lot of times you're going to say find the pressure of this gas, or find the pressure of air, find the pressure of whatever. So it's important that you can relate, that you can translate that the pressure of the gas is P bottom on your equation, okay? So it's very important that you're able to do that. Let me get out of the way again. So really what we're looking for is P bottom, and we're going to write that equation again. P bottom equals P top plus rho GH. P top is the pressure at the top of the column, so that's 0. And density, it says here that you replace the air with something else. It doesn't say anything about the liquid. Actually, it says here it's same liquid. Same liquid means same density. So the density here is going to be the same one we just found. So it's going to be 17,177. Gravity, 9.8. And the height, it says that the height is now 80 centimeters, okay? So if you multiply all of this, you get 1.35 times 10 to the 5th Pascal, pressures in pascals, and this is, my friends, the answer. Now, I want to talk about this a little bit. If you change this into ATM, you don't have to, but I'm doing it here real quick. This is going to give you 1.33 ATM. And let's actually talk about this real quick. So for the first part, for part A, when you had a pressure of gas that was 1 atm, the height was 60 centimeters. Okay. Here we had a different height. The height was 80 centimeters, and that's because the pressure was 1.33 atm. And this should make sense. The first time I had this pressure here, 1, so we did this. On the second situation, this pressure over here is 1.33, so you should expect that the height will be increasing. Okay, so this is a way that you can kind of validate that your answer makes sense. In fact, this difference is proportional to each other. So notice that 80 is 1.33 times more than 60. So if you do the ratios, 80 divided by 60 is 1.33. So if you're 1.33 times higher, that is because the pressure outside, or the pressure of that gas, is 1.33 stronger. Okay, so that's it for this one. Let's keep going.